In this video, we will examine autoencoders as a matrix transformation. We will cover autoencoders as matrix transformations, one-layer autoencoders in PyTorch. A matrix transformation is essentially a function. You take the vector x and outputs a new vector z. It's essentially a matrix multiplication. In some matrix transformations, you can get back to the original vector by finding the inverse matrix. We simply multiply the transformed vector by the inverse matrix. In some cases, we can simply use the transpose of the matrix. This is called an orthogonal matrix, or in the language of autoencoders, tied weights. Sometimes we will denote the encoder with a transpose and the decoder as a regular matrix. Let's describe the matrix transformation using the vocabulary of single-layer autoencoders. The vector x is the input. The first matrix is called the encoder. The vector z is called the code. The inverse matrix is called the decoder. We finally have the output or prediction. Like a neural network, each matrices are weights. Later on, we will see how to get them via training. Let's do an example. Consider the following vector or tensor. It describes a point 3 units to the right and 3 units up. We can describe the point in terms of the standard basis, i.e. the following two vectors. We have the first component that represents the horizontal direction, and the second component that represents the vertical direction. We can represent the point as a linear combination of the standard basis. We can represent the same point with a second basis, the vector u1 and the vector u2, both having unit length, i.e. length of 1. We can find the projection of x1 on u1 and call it z1. This is the projection of x1 on u1. We can do the same for u2. As the vectors are perpendicular, the projection is 0. We can visualize the projections z1 and z2 as a space. We have the original vector, will appear to be rotated. In the context of autoencoders, this will be called a latent or encoding space. We can also reconstruct the vector interims of the new basis. This will also be called the output of prediction. We can represent this process with matrices. The encoder takes samples in the input vector, then maps it to the latent space. The actual output is called the code. The rows of the matrix are the vector we would like to find the projection onto. In our example, we will have the following rows. Using our example, we have the input. The encoder outputs the code. We can represent the process with the following matrix multiplication. The decoder is also a matrix. In this case, the matrix is orthogonal. Its inverse is simply the transpose. The decoder maps the code back into the original space. The columns of the decoder are the new basis. From our example, we have the following. Using the points from the example, we get the following. We can represent the encoder as layers of neurons with a linear activation function or pre-activation, similar to a neural network layer with no activation function. We have the input. The encoder matrix is simply a layer of a neural network. The input dimension is the size of the input. We can see what each element in the matrix represents. The first row of the matrix is the first neuron. The second row is the second neuron. Each neuron has an input dimension in 2. The output space is the coding space or latent space. Each sample is called the code. We have the decoder. This time the columns are the neurons. Each neuron has a dimension of 2. The output of the decode is the vector. Just a note, as PyTorch treats the input as rows, we transpose all the operations. Let's do an example where the code is smaller than the input. If the code is smaller than the input, the autoencoder will store important information about the input x. This is called a bottleneck or undercomplete autoencoder. Let's say we have a 2-dimensional input and a 1D code. We have an encoder. It consists of one neuron that has an input dimension of 2. The output code is 1 dimension. The decoder contains 2 neurons each, with 1-dimensional input. The output has the same number of elements as x, but it's an approximation of x, so we add the hat. Let's clarify this with an example. The input can be any point in the Cartesian plane. We have our encoder. We can represent this as a vector. We have the latent or encoding space z. We have the first input. We determine the code. We can plot the value of the code in the latent space. We have the second input. We determine the code. We can plot the value of the code in the latent space. We repeat the process. Now let's see how the decoder works. We take the code for the first sample. We pass it to the decoder. We get the output. We take the code for the second sample. We pass it through the decoder. We get the output. We repeat the process. We see all points fall on the line of that are a scalar multiple of the decoder. We see that all the data point can be represented on the line. For the most part, this is a good approximation. We can build an autoencoder with matrices, but let's build one with a custom module in PyTorch. This will come in handy when our autoencoders get more complicated and we have to get the weights via training. We create the first linear object. We will set the bias to false. This is not always the case with autoencoders. This is just the encoder matrix. We create the decoder as a linear object. This is also a matrix. We use D because the decoder does not have to be the inverse of the encoder. In the constructor, we put the size of the input dimension. This is the size of the input vector or tensor and the output tensor. Just a note, in PyTorch, the input-output is a row tensor. We have the encoding dimension or the dimension of the latent space. This is the number of dimensions of Z. In the forward function, we call this the encoder. This takes the input X and outputs the code. The decoder takes input Z and produces the output. We create an autoencoder object with an input dimension of 2 and an encoding dimension of 1. As PyTorch randomly initializes the weights, we set the ones used in the previous slides, i.e., where the decoder is just the transpose of the encoder. We output the code by calling the encoder method. We can produce the output by calling the decoder on the code, but this can get tedious. Usually, we just call the forward method directly to get the output. Just like a neural network, we can apply an autoencoder to each sample. Each vector or tensor is a row in the matrix. We can apply the encoder to each sample as follows. Each row is the code pertaining to a different sample. In the same manner, we can generate the prediction output for each sample. The following plot will be created in the lab. The input, the latent space, and the code. Output vector, this is mapped to a point on a 1D line. The output, the vectors, a subspace, is denoted by the line.